Okay, let's get started. Did everybody get the email I sent out? I sent out an email, I want to say it was yesterday, that I have posted on Canvas all 8 of your take-home exams. Did y'all get that?
Yes.
Okay, so normally I just print those out and hand them out, but because of how fast this course is going to go, I just went ahead and provided those to you. So the first one, print it out and go for it, I guess, if you want to go after that first one. Remember, you have to do 4 of the 8. So it's due, I don't even know. Did anyone see one? Yes, it's due not today, I guess that's what I could say. Let's see when that first one is due. The 19th, a week from today. So let me just say a little bit about these mini exams, how I created them. So your homework problems come from the book, and those problems are pretty straightforward. I, again, have all the solutions to all the homework problems worked out on video. So you should never really be stuck on a homework problem, in theory, okay? The mini exam problems are extensions of these ideas. So they are going to be more challenging problems. I expect you to get stuck. I expect for you to need help. I expect for you to reach out. Now, I believe on the first exam, I said you can work together. Let me see. Yeah, I put here, you may work together on this exam. Not every one of them is like that. So on this first one, this would be a good opportunity for you to maybe make some friends in class, work outside of class, try and figure these things out. If you cannot figure it out together, then you should reach out to me, all right? And don't hesitate to do that, yes?
Are all the exams about the same length?
They're not all the same length. Some of them are just a little longer than others, and it just depends,
How long it takes to get through the problems?
Yeah, I know the first ones are pretty dense. I did trim them down from like the normal semesters. They're a little longer, but I tried to trim them down. Like, for example, this first problem here has to do with the plane and the speed of a plane and crosswinds. Like, I'm never going to talk about that in class. Like, I'm not going to give you an example like that. So I expect that you're going to have to do a little bit of thinking, maybe a little bit of Googling of things and, researching, trying to make sure you understand what's going on. Yes?
Are we going to have questions like that in the midterm?
On the midterm exam and the final will be geared more towards your homework problems. So those will be, I guess, less intense, I guess you could say. Yeah, more straightforward. In fact, a lot of the problems on the midterm and final, I will have you setting up problems and not actually computing them the whole way through. So like when we get to like triple integrals or things like that, like I'll have you set up all the integrals and then move on to the next problem. So, because I give you a triple integral, it takes you an hour to do and it's just not worth it. It's more important that you can take the problem and turn it into the mathematics. And because that's the part that the computer can't do. The computer can do triple integrals all day long. So, does that make sense? So you need to make sure you're doing, I guess I'm saying this because I don't want you to get to this and be like, okay, this is part of my grade, my homework's not part of my grade, so I'm just going to do this, and then realize that you don't have the foundation yet because you didn't do the homework. Like, you need the homework to be able to kind of attack this. Hopefully that's in theory the way it's supposed to work. All right? Okay, any other questions on that? All right, so I think last class was a lot of things that people have already seen. I hope that's the way it was. It appeared that way. Hopefully today we'll get into some stuff that's a little bit different or seems newer. We're still not going to do any calculus yet, no differentiation, no integration. That's still not going to happen for a little while. In fact, we won't get to that until next week. All right, that's when we'll start doing integration and differentiation. Right now, we're just kind of setting up the framework, the building blocks, so that we can work in three-dimensional space, and then we'll go do all the cal. All right, so we were talking about vectors last time, basically notation, how we add vectors, subtract vectors, visually what they look like, parallelogram rule, all that stuff. And then we talked about that there are three types of multiplication: scalar multiplication, dot product, and cross product. We started dot product last time, and we talked about how you can use a formula to figure out the angle between two vectors. And now we're going to talk about a very, very nice application of the dot product, and that is this thing called vector projections. And this thing right here will peek its little ugly head at us all throughout the semester. We'll see it later on in chapter 13. We'll be using this. And I'll say, oh, remember way back when, vector projections, that formula, this is what I'm referring to. So the example I'm going to give you right now is a visual example of what a vector projection is. The example is going to be in two-dimensional space, but everything that I do can be extended into three-dimensional space. It's just easier to look at it when it's in 2D. So let's say that we have two vectors sitting here in space. We have a blue vector and a red vector. All right, so remember, these vectors can be, slid over left, right, up, down, right? We just can't change the direction. We can't change its length. Otherwise, they can be anywhere. But let's go ahead and move these vectors so that they are tail to tail, and talk about what's called the projection of the blue vector onto the red vector. So you can see it. Let me make this blue vector a little bit shorter. Do y'all see this purplish vector right here? This is the projection of the blue vector onto the red vector. And I hope it's obvious from your point of view that what we're doing is we're kind of turning our heads and making this like flat, like almost like an x-axis. And we are dropping a perpendicular line from the tip of the blue vector, dropping it down until it hits the red vector, and then drawing a new vector from their tails to where it hits, right? And that is the projection. It's almost like a shadow. It's almost like if you had a light source up here, it would be almost like the shadow of this blue vector onto that red vector. Do y'all see that? So what happens if I make this red vector longer? Is the projection vector going to change? No, it shouldn't, right? If I make this longer, I can't go any further. What if I make it shorter? Still stays the same, right? What if I go shorter than where it would hit? It's okay, okay? So even though this red vector is short, imagine if you extended that vector, right, in both directions forever. The projection of the blue onto the red is going to result in a new vector that is actually longer than the red vector in this case, right? And then what happens if I take this red vector and I point it in the opposite direction? Same thing. The projection vector is still like a shadow onto this imaginary dotted line created by that vector. Does that make sense? Yeah. Okay. Now, that's projecting the blue one onto the red one. We can do it the other way around. We can project the red one onto the blue one. So now we kind of have to look at it and like this is it, and we want to drop here perpendicular down to the blue one. So it'd look like red onto blue. There we go. Okay. So given any two vectors in either two or three-dimensional space, we should be able to project a vector onto another vector. All right. And the order matters, right? If we're projecting blue onto the red or the red onto the blue. We get two different answers, don't we? Okay, so what is the formula to find that vector? What is the projection formula? And here's what we have. First of all, the notation. PROJ stands for projection, and then subscript V, and then regular script U. This notation means we are projecting U onto V. So this would be like the blue vector onto the red vector. So whatever's down here in the subscript is what you're projecting onto, and then whatever's here is what's being projected. All right? So I always look at it as like, you know, whatever's subscripted down on the bottom is what I'm projecting onto. And here's the formula right here. This is it. This is how you find the projection vector. And look at this formula. I know it looks weird, but I mean, let's just discuss what these things are. First of all, look at this right here. I'm projecting U onto V, right? U is going on to V. So my answer has V in it, right? The vector V. And so look at all the stuff in front of it. When you take V and dot U together, what does that give you? If you take the dot product of any two vectors, what does that give you? Is it a vector? Is it a number? What is it? It's a number, right? So this is a number. The dot product of V and U is a number. And then this is the length of V, right? Squared. That's a number. So you have a number over a number, which is a number, and then times V. So this is telling you that you have some scalar multiple of V, which corresponds to the geometry we saw. When you go and you project this blue one onto the red one, your answer, this projection vector, is parallel to the red one, isn't it? Yeah. So therefore it must be a scalar multiple of it. And so how long this is completely dictated by this quantity right here. All right? So that's what I'm saying here in the notes, is that the projection vector gives you some scalar multiple of the vector you're projecting onto. All right? So sometimes we actually, when we project a vector onto another one, sometimes we don't want the answer to be a vector. Sometimes we just want to know how long that vector is. And so you get a different definition, which is called the component of U onto V, or the length. It's just the length of the projection vector. So when we have the projection vector of U onto V, if we wanted to know how long that vector was, just its length, that is this thing. That is the component of U onto V, right? You all understand the difference between the two? Projection is a vector, a scalar multiple of what we're projecting onto, and the component is just how long that vector is. And look at the formula for this. The formula for this is just this, right here. Okay? This is the length. So it's a very, very nice computation to figure out the length of a vector that's being projected onto another one. You just take the dot product of two vectors and divide it by the length of the vector you're projecting onto. All right, let's do an example. Okay, so these are the vectors we're doing. You know what? Maybe we should do a three-dimensional example. Do I have one? No, I don't have one. There we go. All right, so we have a vector U, which is the vector 2, 4, and the vector V, which is the vector -3, 7. These live in two-dimensional space. And let's first do the projection of U onto V. So the formula for this is V dot U over the magnitude of V squared times the vector V. So let's do some scratch work here. What's V dot U? -6 plus 28. So 22. Okay. So that's from last class. And then we need the magnitude of V. Let's get the magnitude of V, which is the square root of the square of each component. So negative 3 squared plus 7 squared. So this is root 49 plus 9, right? 58.
Because it's squared, wouldn't you just give it the square root?
Yeah, when I get back to the formula, the square root's going to go away. All right, so we have over here 22 over the magnitude of that squared, which is 58, and then times V. But what's V? It's that vector negative 3, 7, right? So negative 3, 7. So this is equal to, this is scalar multiplication, so we could distribute this through, and we get something like negative 66 over 58, comma, what is that? 154 over 58. There we go. All right. So it does say to sketch the results. So let's just do a quick sketch to see if our answer makes sense. Just let me sketch our two vectors. Okay, let's sketch the vector u, which is 2, 4. So I'm going to go to the right 2, not 4. So right there, I have a vector. I'm going to start it at the origin, go there. That's u. And then v is negative 3, 7. 4, 5, 6, 7. There's v. And then where's my projection vector? So somebody on their calculator, please give me these as decimals, and we'll just round them. What is that? 66 divided by?
49.65.
What is it?
49.65.
0.9? No. This one? I think you did it backwards. Negative 1.13. And then this one, it's about what? 2.65. Are you all with me? This is very mechanical. We're not doing anything crazy here, right? This is, all right. Negative 1.3 would put me about, I don't know, negative 1.3 here, and then 2.6, 2.6, somewhere in there. I'm doing my best here, okay? And then it's that vector. Does that look like the projection of u onto v? Yeah, it does. I mean, it's not bad for just drawing it on the board, right? Without any real reference. If we take u and project it, right, perpendicular projection, shadow from a light source right here, we should get this vector. All right. Now, what is the component of u onto v? Now, I could use the formula, couldn't I? But I already have the projection vector right in front of me. So why don't I just take its magnitude, right? So the component of u onto v would just be the magnitude of this vector, which would be the square root of negative 66 over 58, that thing squared, plus 154 over 58, that quantity squared, whatever that is, all right? I'm not going to do the computation. We don't need to. All right? Straightforward? The next example, example 10, oh, is that a typo? Did I just do the same problem? Or?
No, you switched the.
I switched them, right? So look, now I want the projection of v onto u instead. So I don't think I'll work through this one, but do you understand that slight change in the notation means that our formula is going to change. How would this formula change? We won't do the work, but how would our formula, what would it look like now for projection? Projection, this would be v here and u here, right?
Correct.
And so this would be u dot v over magnitude of what squared?
U.
Magnitude of u squared
Times.
times u. Okay, so that would be the difference in the formula. So everything kind of switches places. And I think you could handle that. All right, moving along. I'm giving you a chance to read that. Where's my little rag? There it is. Given a three-dimensional vector, u, you're asked to find a vector v such that the component of u onto v is 3. Let's try and understand this. Let's try and understand this visually. All right, we're given a vector u in three-dimensional space. So imagine that, the origin is over here, right? We've got this vector coming out from the origin. Let's just say this is it, all right? This is our vector u. We're supposed to find some vector v so that when I project, which one onto which one? When I project this one onto this vector v, that the projection of that, so like the shadow of it coming down onto this one, has a what of 3? Projection? Component, a length. So the length of that shadow here is 3. My question is, do you think we're going to have a unique answer, a single vector answer? No? Why not? So let me do it this way. Let's make this one the u, okay? This is our u sitting out here. And then we're trying to find some vector v so that when we project this onto this one, we get a length, the length of that projection is 3. You're saying no, that it won't be, there's not just one unique answer?
Yeah, that's what I'm
Okay.
saying.
Does everyone see that it wouldn't be?
Yeah.
What would be another vector? Let's just say that the projection of this onto this is 3 right now. What could I do to find another one?
Slide the ruler back and forth. Repeat the direction.
Like this?
No.
The projection would still be the same. This vector, so it would be a scalar multiple, I guess is what you're saying. Who said that? I just heard it. So you could change the length of this, right? And that would give you would have the same projection, but they would all be scalar multiples? Like if you slid this back and forth and made it longer or shorter, the answer would all be scalar multiple of the same thing, right?
Yeah.
But I'm saying, is there something else?
Yeah, as long as you keep the angle between them the same.
If I keep the angle between them the same, imagine going around this thing like this. Can you all see that? If I go around this like this, that projection should be the same. So it's almost like this cone around this thing, isn't it?
Yeah.
Okay. All right, well, let's see. So let's see what we need. We need to find a vector v such that the component is equal to 3. How in the world do I do this?
Use
Go
the
ahead.
formula for the-
Yeah.
Use the formula for the component and then plug in what you know and try to work backwards.
Okay, so what is the formula for the component of u onto v?
U dot v over the length of v.
Over the length of v. We know that that must equal 3, right? Okay, we know that much. Right? That's this right here. That's what this is saying. The component of u onto v must be 3. And we know what u is, right? We know what u is, but we don't know what v is. So since we don't know what v is, let's make up an arbitrary v. In other words, let's say v is equal to some three-dimensional vector, right? We don't know we don't know what the components are. We call them v1, v2, v3, right? So that's what v is. We're trying to figure out what that v should be to make this thing true. We know u is already given to us as 4, 0, -1. So if we use these two pieces of information over here in this equation, let's see what we get. So what would u dot v be?
For V1
4v1,
plus, oh, 0.
so plus 0,
Yeah,
and then minus v3. That would be on top, wouldn't it? Now, the magnitude of v on the bottom, which is the square root of v1 squared plus v2 squared plus v3 squared, that all must equal 3. And at this point, this should tell you right now that you are not going to have a unique solution, because you have a single equation and you have how many unknowns? You have 3 unknowns. So 1 equation and 3 unknowns. So there's no way you can get a unique solution, right? So what hope do I have then? I'm just supposed to find any v, right? This doesn't say for me to find every v. It just says find v such that this is true. So let's go and try and figure out one particular v that would work. So how could I go about that then? What could I do? What do you mean?
U as a hypothesis.
Set up a right triangle. Well, you mean like draw it out? Not quite.
U as a hypothesis.
Make,
Mhm.
you can make
3 as one of the legs.
Mm-hmm.
And then.
No, I think I know what you're saying. You're saying we know the length of u, right? We know that the shadow on the ground has to be 3, so we should be able to solve for that other side, right? But will that help us get a specific vector? All that will get us is that one side. Does that make sense?
Yes.
So I'm not quite sure how that tells me which way anything is pointed. Yeah. Okay, well, let's table that. Let's see, we might come back to that.
I don't know.
You-
We could set up, we can make the numerator 3, and then that would define 1 and 3, and then we could just find a V2 that would make the bottom one 1.
Oh, so you're trying, okay, so you're trying to solve this equation, and you realize that you have some control over these. Since there's 3 variables, 3 unknowns, and 1 equation, you can kind of fix 2 of them and try and go after the third one.
Yeah, that's what I was playing.
That's what you're saying too?
B2 is what I was playing with.
Yeah, remember, all we want here at the end, my final answer is I need somebody, or we need to figure out a V1, V2, and V3, right? There's an infinite number of answers possible. I'm just looking for one of them. So the suggestion here is, why don't we make this become 3? And I think that's because that's 3, and then it'll, yeah? So if I make this 3, then that's going to have to be 1, isn't it? Yeah. Okay, so let's go with it. Let's see what happens. How are you going to make that 3? Your choice.
I guess I can make V1,
You want to let V1 be
1,
1, and then let
V2,
V2 be 1. Is everyone okay with that? Sorry, 3. 3? Right.
V3 equals 1.
Oh, sorry. V3 is 1. I know exactly what you're doing. I'm about to see if anyone disagrees at this point.
Isn't it gonna, it won't work because V2 is gonna end up being an imaginary number?
Yeah, so look, I know what we're trying to do here. I agree with the method. The method is trying to make this 3 because it'll match with that side and it'll just make everything nicer. And by making this 3, we would need to let V1 and V3 be 1, each of them 1. But if that's 1 and that's 1, right?
yeah.
Then we would need this to be 1, right? If that's going to be 3, this needs to be 1 so that it's equal. But if you make that 1 and that 1, there's no way that this down here could be 1. Yes?
Yeah.
So, do you all follow that? Sure?
I got that.
Let me just write it down. If we write 4 minus 3, 4 minus 1. God, keep doing it. Let's just keep going with this. I want to make sure everyone sees the problem. If I just replace right now, we get this over square root of what? 1 plus v2 squared plus 1 squared. So this will become 2 plus v2 squared, right? That's what the bottom will become. This equals 3. So this is 3 also, right?
Yeah.
So divide both sides by 3. We get 1 over square root of 2 plus v2 squared equals 1. And then you can multiply both sides by the radical, and you get 1 equals square root of 2 plus v2 squared. And this is not going to happen because it's impossible to make this thing 1, right? You need this right here to be 1 in order for this to be true.
Yeah.
And 2 plus a positive number, because it's being squared, not going to happen. So I like the idea here, but I think our choice of v1 and v3 won't work, right? So we need to maybe have a different choice. Yes?
Just off of this document, this suggestion. What if we make 3 a larger multiple, a larger multiple of 3, say 12 in this case? Make it 12 instead.
What? Change this
Yes.
to 12?
Yes, change it to 12 and then be able to, and then with that, you'd be, that possibly, not that to 12, but.
Are you asking me to change the problem to 12? Or are you...
What I'm trying to say is, basically trying to change that, instead of having 3, make it 12 over 4. Sort of along the line, make it a fraction so that you have some.
Okay, yeah, now I see what you're saying.
From the top and the bottom.
Yeah. So whenever we run into an issue like this, we want to sit here and think about what was the problem that we had. The problem was that at some point we were trying to make this radical equal 1, but it was impossible because of what was underneath it, right?
Yes.
So I think what you're suggesting is instead of making these things like a 3 and a 3 cancel, maybe we can make this something where when we cancel them, we're left with, where do you want it to be big? Do you want it to be big over here or over here? I guess that's, you want this big? Maybe we should do this. Okay, there. So if we divide both sides by 3 right now, we're here, right? So we know that this right here has to be a positive number, right? And we need to somehow pick, we don't even have to do v1 and v3. We could do v1 and v2. We could do v2 and v3. It's our choice. But we need to somehow make this work. I think what you're saying is that you want to make this maybe like a 12 so that this becomes a 4, and then maybe that'll work.
Yeah, sort of on that line.
Yeah?
But when you put it like that, there's like, I think another way to do it now. But
Yeah. So what do you want to do?
Put everything equal to V2, possibly?
So make them all the same?
No,
V-
we can make the variables there and then put everything equal to V2, giving you a formula for that.
Oh, you mean come up with an actual solve for V2?
Yes.
If we solve for V2, it'll be in terms of V1 and V3, and then maybe we can look at that and we'll know what works and doesn't work,
Yeah.
possibly.
Yeah.
There's a possible solution if we make V3 to 0.
Yeah, I like the idea of V3 being 0. I'm not sure if it's going to work, but let's just think about why that logic might make sense. If V3 is 0, then you don't have to worry about it contributing anything on this side, right? It's going to go away. It's going to go away right there, right? So let's start with that. If V3 was 0, let's just rewrite what this equation looks like. Let V3 be equal to 0. Then we have 4V1 over 3 equals square root of V1 squared plus V2 squared. Right, that's where we would be? All right. Now, does it seem like we can make this work?
Yeah.
I think we can, because what would be a good candidate for V1 right now? I mean, anything would work. Well, not anything, but remember, we don't want this to get too big over here, right? So, I don't know. How about 1?
Yeah.
Will 1 work? Because if I do 1 here, this is going to be 4/3, right? And then I'm going to have here 1 squared, which is 1. And so I'm trying to keep the square root of 1 plus something smaller than, or equal to something that's bigger than 1. So this would probably work. Let's try it. Let V2, or V, what is it, V1? V1. And now we get 4/3 equals square root of 1 plus V2 squared. Now we should be able to make that work. Let's go ahead and continue. How do we continue that? Square both sides?
Yeah, square both
Okay,
sides.
so remember that when you square both sides of an equation, what's the catch? There's a give and a take to that. What is the thing you have to worry about when you square both sides of an equation?
That's what mine is.
That's when you square root both sides. When you're allowed to square both sides of an equation, right? We all agree?
Yes.
Oh,
But-
you're squaring by it.
But
Wouldn't there be a middle variable in there?
a what?
A middle variable since you're squaring the binomial?
Mm.
Oh, it's not a binomial.
No. Here's what I'm getting at. Take that equation, okay? Do we all know the answer to that? X is 4, right?
Yeah.
Okay. Now, if I square both sides of the equation, what would I get?
You get.
X equals 4, right? No problem? There's no problems with that, right? No problem. We square both sides, we got the right answer, okay? We don't see any issues here. Let me do a different one. I know this isn't gonna make a whole lot of sense, but there's an equation, right?
Yes.
Okay, I'd like for you to square both sides. What would you get if you square both sides? Okay, now go back and tell me what X is. So imagine I didn't tell you that, okay? Like, say we didn't know that. If you square both sides of an equation, then you try and go back and solve, what are the solutions to this? Plus and minus 2, right? In other words, when you square both sides of an equation, you always have to remember that you introduce the possibility of extraneous solutions. So whatever we get here, we're going to have to check. We have to check our answers. Because if there are answers, they'll be in here, but there could be answers that don't work. All right? So just remember that when we square both sides, we're going to have to check. Now what? Just solve, right?
Yeah.
It's pretty straightforward. So we subtract 1 on both sides. What do we have there? 7/9 equals V2 squared. And now take the square root. When we take the square root, we have plus or minus root 7/3. I just root of top and bottom separately. And there are our 2 candidates for our V2. So how do we check it? Where do we check it?
Go back to the formula for the component.
Yeah, we have to go back to the point before we squared, which is right here. And we just have to make sure that both of those give us the right result. And fortunately, because it's squared in here, it's going to work. So if you plug in root 7/3 here, square it, you get 7/9 plus 1, and then take the square root. It should work. So both work, right? So at the end of the day here, our final answer to this is V is, what was our V1? It was 1. V2 was, let's go with the positive 1. And V3 was 0. So that is one particular V where if you take the component of U onto V, you will get a length of 3. But it is not the only answer, all right? Questions at all?
So that's the only way to go about it, just plug it in.
You could get a general answer that would be an equation with 3 unknowns. You would have Well, do you know the equation we had just a second ago before we plugged in V1, V2, V3?
Yeah.
Right?
4v1.
Yeah, all that right there. If you could clean that up and make it a single equation, and that would turn out to be the equation of a cone. Okay? So we could give, it's like we could give the answer as an equation, just like if we wrote this down, x squared plus y squared equals 9. I'm telling you that these are all the points that lie on a circle of radius 3. Right? That's what this represents. In two-dimensional space, this is all the points on the circle of radius 3. We could have kind of left our answer with all the variables in it, and we would need to recognize that that is the equation of a cone in three-dimensional space, which in Chapter 10, Section 5, I believe it's Section 5, we are going to talk about what are called quadratic surfaces. So we will look at equations of cones and spheres, and, well, we've already done spheres, hyperboloids, and different three-dimensional surfaces. So, but right now, I don't think we would recognize it. Does that answer your question?
So what I'm saying is, like, would that be the answer? As like you couldn't leave it as the equation of the answer. You have to plug in to find an actual vector with the. Like,
If this said find all v such that that's true, then we would have to leave our answer in that equation form. So like we could solve for one of the variables, but we couldn't get a nice, like, there's not one answer, so it would have to have variables within the vector. I don't think I'm making sense. 4v1 minus v3 over square root of v1 squared plus v2 squared plus v3 squared equals 3. The best we could do is solve this for either v1, v2, v3, right? And then write our vector as, okay, v1 is something, v2 is something, and then v3, we would have to solve this thing for v3. Solve it for v3 and plug that in right there. And that would be a general form. It would be v1 is something, whatever you want it to be, v2 is whatever you want it to be, and v3 is some combination of those two things. Or you could solve it for v1, put it here, and then leave v2 and v3 free. But that's why I didn't ask you for the general answer, because it would get too complicated right now. For just an in-class example, that's too complicated. All right, so those are the homework problems for that section. All right, we're going to move on to 10.4. Are there any computer science majors in here? CS? Okay. I'm asking because the stuff that all these things that I'm doing here, these notes and these animations, like things like this, I'm using Mathematica. Everyone here has heard of Wolfram Alpha, right? I don't think you can be alive and not know that anymore. So Wolfram Alpha, when you go to Wolfram Alpha and type something in, it sends that problem to some server and it spits back your answer, right? So the server is using as its kernel, as its brains, right, this program Mathematica. So this is the brains behind Wolfram Alpha. So you can purchase this program and you can code up your own stuff. So if all these animations that I do are just codes that I've written for these things. So if you're interested, if you're a CS major and you're interested in this sort of thing, I'm more than happy to share my code with you, all right? If you're interested. It's like a C+ based language, and there's so many built-in functions. I'm basically not really coding, But you can like do like real like do loops, for loops, all that stuff. If then, yeah, it's there. Okay. Cross product. So remember this notation, the IJK, right? I said I don't use it very often. IJK notation. Okay, so now we're going to talk about the cross product. So remember, dot product gave you a number, right? Cross product between two vectors gives you a vector. So you start with two vectors, spits out a vector. Does anyone know what the most important property of that vector is? I know most of you have seen cross product before, but what is, maybe you can help emphasize for the students who have never seen the cross product before. What is the most important thing when you take two vectors and you take their cross product? What is the biggest thing that we get from that, the answer? It's a vector, but what's its most important property?
Its direction.
Yes, what about its direction?
The normal vector.
Normal to what?
So both of them.
Okay,
It's orthogonal to both of them.
that's right. Okay, so if you take one thing away from cross product, the one thing you have to take away is this. If I start with a vector, and then I get another vector and I put them tail to tail like this, then I'm actually defining a plane, aren't I? Like you all see that plane right there? When you take the cross product of these two vectors, you're going to create a new vector. And that new vector will be perpendicular to both this and this. In other words, perpendicular to the plane. So it's perpendicular to both vectors simultaneously. So the vector that comes out when I cross these two would be something like this, coming out towards you like that. Now, it could also be on the other side going out away. It depends on the order in which you cross them. And it's based on the right-hand rule. So let's say this is the vector u, and this is the vector v. And I do u crossed with v. Then I get my right hand, point my fingers out u, curl towards v. My thumb points in the direction of the cross product vector. So in that case, u crossed with v, I would get that vector. What if I did v crossed with u? V crossed with u. This time, my fingers are over here, curl this way, thumb pointing out this way, it would go out that way, okay? So that, I'm about to basically say everything I just said here in these notes. Where's my picture? Here we go. It's hard to see it three-dimensionally, but there's the best I can do. I have two vectors. It's the blue one and the red one. And I hope that you can tell there that their cross product is that black vector, that you can tell that it's orthogonal to both. Does it look like that to you? I can change the red and the blue one. I can just arbitrarily change where they are. Let me just do that. And then we'll see, we'll look at the black one and we'll see if it looks orthogonal still. So I just changed my two vectors I'm crossing and kind of, there we go. So does it look orthogonal to the blue one? Does that look like a little 90 degree? Yep. If I roll this around, it looks like it's also orthogonal to the red one, perpendicular. So that is the main property. Now, how do you do a cross product? What is the actual computation, right? We know how to do dot products. That's easy, right? Formula for dot product, super easy. Cross product, what do y'all think? Not as easy, easier? Those of you who've done them know that it's a little bit more involved, right?
It's the long one, right?
Yeah, well, it depends. There's different ways that it's taught, okay? So I'm going to choose to just teach you a way that I like that students pick up pretty quickly. So hopefully you do it this way. If you already have learned cross product and you're happy with the way you do it and you don't like this way, then use your way, all right? So here's the way it works. Let's take two vectors. I'm just going to do an example here. Let's take 4, -2, 1. And let's take the vector -3, 5, -1. And let's cross these two vectors. So the notation we use for cross product is U with a, almost like a multiplication symbol, but it's not. It's a little cross, a little X. As opposed to the dot product, which is a little bolded dot, this is like a bolded X. All right. So that's the notation. Mechanically, here's how we're going to do it. We're going to write the vector, just write this down first, and then you'll see what I'm going to do. So write ijk, all right? And this is kind of like a shortcut to doing this. 4, -2, 1. Write down the components of the first vector, u, and then the second vector, -3, 5, -1. How many of you have seen something like this? Yeah? Okay, good. Then you can tell everyone how to do it.
I like the other way better,
You like the other way?
the long way. 'Cause this
Oh,
way-
where you write it
Yeah,
twice?
this is the one with the lines, right? Or where you go like from up, left, and down.
Yeah, I don't know. Let me just do it. Let me show you how I'm going to do it. Yeah, because at this point, still, it could go different ways. All right, does everyone here know what a determinant of a 2 by 2 matrix is? You have to know that also, okay? So a 2 by 2 matrix, if someone gives you a matrix, A, B, C, D, the determinant of this is what? A times D minus these two multiplied, B times C. So it's a very straightforward computation. You go this times this minus this times this, and you're done. That's what a determinant of a 2 by 2 matrix is. What we're going to do here is we're going to use this same computation to calculate what's called the cross product. So what we're going to do is we start here, and our answer, okay, our answer to this cross product is a vector, right? Our answer is a vector. It has 3 components to it, right?
Yes.
The first component comes from covering up the first components here. Okay, you cover them up, and then you do the determinant of that little 2 by 2 matrix. All right? So what's the determinant of this 2 by 2 matrix? This times this, 2 minus 5. 2 minus 5. I'm going to write it down. 2 minus 5. Okay. That seemed pretty straightforward there?
Yes.
Okay. How do we get the middle component?
Cover up J.
Cover up J. And then this is the part that it just depends on how you learn it. You see that we still have a 2 by 2 matrix?
Yeah.
The way that I tell people to do is just do the determinant again. Okay. So what do you get? 4 times that is what? -4?
Yeah.
-4 minus what? -3. So I'm going to write that down. -4 minus -3. Isn't that what it was?
Yes.
However, there's a big asterisk here. When you do the middle one, you have to change the sign at the end of the day. Like you have to take whatever answer you get here and change its sign. All right? And then the last one, you go here, and then you do the determinant on there, and you don't have to worry about changing the sign. All right? So what's that one going to be? 20 minus
Minus 6.
-6. So 20 minus 6. And that's it. So what is the cross product of these two vectors? -3. What is it? +1?
Yes.
And 14. There you go. Now there is a formula for it. Like that's not a shortcut like that. You can go learn it if you want. I'm not going to teach it. It's in the notes. It's in the book. We want to be able to do cross products very quickly. So we just want to be like covering determinant, cover determinant, change the sign, cover determinant, done. All right? What is V cross U? So does the order matter? With dot product, did it matter?
No.
With cross product, it will. Okay? But all it's going to do is change the signs. So it's going to be positive 3, negative 1, negative 14. And that has to do with what I just said about the right-hand rule. When you cross two vectors, you're going to get a vector that's perpendicular to both. One of them is going to point one way. If you cross them the other way, it points the other direction. So it's just multiplying it by negative 1 to flip it over. So the cross product the other way is this way. So here, what would we do different here if we were trying to do V cross U?
Put V up.
Yeah, you just switch, you put this here, this here, this here, switch them, and then everything would turn out opposite. Are y'all okay with that, me like covering up thing? Was that close enough to the way you've seen it? Okay. There's another way to do it. I don't want to confuse you, but there's another way to do it. This one right here, determinate, we're okay? Nothing we have to do special. This one right here, we have to do the determinate and then change the sign, right? What you could do instead is a reverse determinate. Do your determinate backwards. In other words, instead of doing this times this minus this times this, do this times this minus this times this. And it has the same effect because it changes where the minus was. So whatever. I'm going to stick to the way I showed you initially. Now, what was the property that I said the major property of the cross product of two vectors? Is that vector that you get is what? Both these vectors are what? 90 degrees perpendicular or orthogonal. And all three of those words will mean the same. To what, though? Like this vector right here is perpendicular to what? Both of these, right? Both of these. And that means, how could I check that? How could I check to see if it's true? Is this really perpendicular to that? Do what? Just take the dot product. If I take U and I dot it with this, what should I get? 0. Let's check it. What is U dotted with U crossed with V? Let's see. Dot products are super easy to do, right? So I would do 4 times negative 3 is negative 12 plus negative 2 times 1 is negative 2. And then the last one would be plus 14, right? That's 0. And you can check it that if you dot V with the same thing, you should also get 0. Right? So V dotted with U cross V should also be 0. So it checks. It's orthogonal to both. That is not a coincidence. That is the defining property of the cross product. And that will be extremely useful to us. What about if you have a vector? Well, let me put it up here. Let me see what you think. What about this? U is equal to the vector 2, 4, and V is equal to the vector negative 3, 5. And I ask you for U cross V. So what are you going to tell me in that case?
And then just see what you make the matrix. So if 2 by 2 matrix.
Yeah.
When working the same way as that, just using cross product between both of them.
So are you saying set it up, the cross product definition?
In the same way, except instead of having I, J, and K, you just have I and J with the 2 beneath it.
With just 2?
Yeah.
You wouldn't be able to.
We have a problem here. Think about the. Do you want to say who? What?
I was going to say, why don't you just put a 0 in place of 5?
Okay, so yes, and that's because look, the way it's presented here, our vectors are living on a flat